The discovery that would forever change astronomy came in 1992, when Alexander Wolszczan and Dale Frail announced the existence of planets orbiting the pulsar PSRB 1257 plus 12. This was not only the first detection of planets around a pulsar, but also the very first confirmed discovery of exoplanets anywhere in the universe. What stunned scientists most was not just that planets had been found beyond the solar system, but that they were orbiting a neutron star, an object born from the violent death of a massive star. These planets, later nicknamed Draugr, Poltergeist, and Phobeter, showed clear evidence of being Earth-sized bodies moving in stable orbits around a dead star. This was baffling, because conventional wisdom suggested that the supernova explosion that created the pulsar should have annihilated or ejected any nearby planets. Yet, against all odds, here they were, 3 stable, rocky worlds tightly bound to the remains of a star that had once exploded with unimaginable force. This discovery not only opened the door to exoplanet research, but also forced astronomers to rethink everything they thought they knew about how planets could form and survive in the most hostile corners of the cosmos. The revelation of planets orbiting a pulsar left astronomers grappling with the very nature of the host star itself. To understand why the discovery was so shocking, one must first appreciate exactly what a pulsar is. Unlike the life-giving warmth of stars like our Sun, pulsars are remnants of stellar destruction. When a massive star, many times heavier than the Sun, exhausts its nuclear fuel, it can no longer resist the pull of gravity. The star collapses in on itself, triggering a supernova, one of the most violent explosions in the universe. In this process, the star's outer layers are blown into space, but its core is compressed into an ultra-dense object called a neutron star. If this neutron star happens to spin rapidly and has an intense magnetic field, it becomes a pulsar. Pulsars are among the most extreme objects known in astrophysics. They are small, only about 20 kilometers across, roughly the size of a city. Yet, they pack more mass than the entire Sun. This means that the matter inside is so densely compressed that a single teaspoon of it would weigh billions of tons on Earth. They spin at incredible speeds, sometimes rotating hundreds of times per second, and their magnetic fields are unimaginably strong, billions or even trillions of times stronger than Earth's. These magnetic fields channel streams of charged particles, which then emit beams of electromagnetic radiation. Because the pulsar rotates, these beams sweep across the cosmos like the rotating beams of a cosmic lighthouse. If Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation, hence the name pulsar. The precision of these pulses is one of the most fascinating qualities of pulsars. They are so regular that astronomers often compare them to cosmic clocks. Some pulsars keep time more accurately than the best atomic clocks built on Earth. This regularity is not just a curiosity. It's the very reason astronomers were able to detect planets orbiting PSRB 1257 plus 12 in the first place. When the arrival times of the pulses shift slightly, it means that something is tugging on the pulsar, something massive enough to alter its motion. That something turned out to be planets. Thus, the very mechanism that defines pulsars as rotating remnants of stellar corpses also became the method by which the first exoplanets were discovered. But while their pulse-like emissions allow astronomers to make precision measurements, the environment around a pulsar is anything but calm. The beams they emit are made up of high-energy radiation such as X-rays and gamma rays. These are not gentle streams of light like the rays from our Sun. They are intense blasts of deadly radiation that can sterilize anything in their path. For a planet orbiting close to such a star, this means constant exposure to radiation powerful enough to strip away atmospheres and boil away surfaces. It is the sort of cosmic environment that should make planetary survival impossible. And yet, this pulsar hosts not just one planet, but an entire system of them. This contradiction is what makes pulsar planets so extraordinary. They exist in one of the harshest environments imaginable, orbiting stars that are no longer truly alive in the stellar sense, but are instead the remnants of destruction. The fact that planets not only exist there but can remain in stable orbits defies traditional expectations of planetary formation and survival. It is like finding fragile glass ornaments still intact in the aftermath of a building demolition. To fully grasp the strangeness of pulsar planets, one must consider the ferocity of their host star's environment, which is where the true paradox begins to unfold. The discovery of planets orbiting this pulsar becomes even more astonishing once we consider the kind of environment such a star creates. Unlike the Sun, which radiates a relatively steady stream of visible light and solar wind, a pulsar is an engine of extremes. As it spins, it hurls beams of high-energy radiation into space, streams of X-rays, gamma rays, and charged particles that sweep across the cosmos with clockwork precision. Astronomers often compare this phenomenon to the rotating beam of a lighthouse, but in truth, the comparison hardly does it justice. A lighthouse guides ships safely to shore, while a pulsar's beams are more like weapons of cosmic destruction, searing everything caught in their path. For any planet in close orbit, these beams would be a death sentence. High-energy radiation has the power to strip away an atmosphere molecule by molecule, blasting it into space. Even planets with thick atmospheres, far denser than Earth's, would eventually be left barren and exposed under such relentless bombardment. The radiation doesn't just target the sky above, it penetrates the surface, sterilizing rock, vaporizing volatiles like water, and erasing any chance of maintaining Earth-like conditions. In the environment of a pulsar, atmospheres are not protectors. They are liabilities, shredded away until nothing remains but bare rock. Adding to this nightmare is the pulsar's wind of charged particles, sometimes moving at near light speeds. These particles, accelerated by magnetic fields billions of times stronger than Earth's, create a constant hailstorm of subatomic shrapnel. Such conditions would tear through any planet's magnetic shield unless it were exceptionally strong, exposing the surface to continuous radiation. The pulsar's immense gravitational pull further complicates things, ensuring that anything orbiting too close is stretched, heated, and potentially ripped apart by tidal forces. This is not a calm star system where worlds quietly orbit. It is a hostile arena where survival seems implausible. Yet, despite this violence, the planets around this pulsar endure. Their orbits remain stable, their structures intact, and their very existence mocks our assumptions about what environments are too hostile for planets. This forces astronomers to confront an uncomfortable truth. The universe is far more resilient and resourceful than we often imagine. Planets are not only products of peaceful, nurturing environments like our solar system, but can also be forged or endure in the wreckage of cataclysmic destruction. The pulsar's environment may look like the very definition of a planetary graveyard, yet here it has become home to an entire family of worlds. Understanding this paradox requires us to look more closely at the system itself, where multiple Earth-sized planets continue to orbit in defiance of astronomical expectations. The survival of these worlds within such an environment has led scientists to study this pulsar system in extraordinary detail, as it provides the clearest window into how planets can persist in the shadow of cosmic violence. The planets discovered around PSRB 1257+12 were so surprising and so unprecedented that astronomers eventually gave the system a nickname worthy of its eerie, death-defying nature, the Lich system. The name comes from folklore, a Lich being an undead sorcerer that clings to existence beyond death. It is a fitting title, because just as a Lich is neither fully alive nor entirely gone, this system is not hosted by a living star, but by a stellar corpse. The pulsar is the remnant of a once massive star that exploded violently, yet in its ruins exists a collection of planets orbiting steadily, as if refusing to perish alongside their parent. The Lich system has become one of the most iconic examples in all of exoplanet science, because it proves beyond doubt that entire planetary families can form or endure in environments that, by all conventional expectations, should be utterly hostile to their survival. The Lich system contains 3 known planets, all of which orbit at distances comparable to the inner planets of our solar system. The smallest of these, Draugr, is only about twice the mass of the Moon and is the lowest mass exoplanet ever confirmed. It sits incredibly close to the pulsar, completing an orbit in just over 25 days. Despite its tiny size, its discovery was groundbreaking because it revealed just how sensitive pulsar timing measurements could be, able to detect a world so small and fragile in such a hostile place. Next in line is Poltergeist, a planet roughly 4 times the mass of Earth, orbiting a bit farther out with a period of 66 days. Beyond that lies Phobiter, a planet slightly larger still, circling the pulsar every 98 days. Together, Poltergeist and Phobiter form a pair of Earth-mass worlds that dwarf Draugr in size, Yet, all three remain gravitationally linked to their dead host star in a surprising display of stability. What makes the Lich system so astonishing is not only the presence of these planets, but the fact that their orbits show remarkable precision. Despite the catastrophic origins of the Pulsar, the gravitational arrangement of Draugr, Poltergeist, and Phobiter remains delicately balanced. Astronomers have studied their interactions closely, noting that their orbital resonances, subtle gravitational tugs they exert on each other, create measurable patterns in the pulsar's timing. This level of orbital stability strongly suggests that the system has been in place for billions of years, quietly enduring in a region of space where nothing should survive for long. It challenges the assumption that pulsar planets are transient anomalies. Instead, the Lich system demonstrates that entire planetary architectures can persist around dead stars for cosmological timescales. The Lich system also became a testing ground for scientific imagination. Could these planets have survived the original supernova, or did they form later from the wreckage? If they endured through the explosion, it would mean that planetary cores can withstand the most violent stellar death throes imaginable, somehow avoiding being incinerated or blasted into interstellar space. If, on the other hand, they formed after the supernova, they would represent a completely new mode of planet formation, worlds born not from the gradual accretion of dust in a protoplanetary disk around a young star, but from the chaotic fallback material of a dying one. Either scenario forces scientists to expand their theories about the environments in which planets can exist. What makes the Lich system even more remarkable is its role in the history of astronomy. Not only was it the first system of exoplanets ever confirmed, but it also instantly demonstrated that planetary systems come in astonishing diversity. Before 1992, many astronomers suspected that other stars might host planets, but the evidence was elusive. Most thought the first exoplanet discovery would involve a sun-like star, perhaps with a gas giant similar to Jupiter. No one predicted that the breakthrough would come from a neutron star pulsing radio beams across the galaxy. The Lich system, therefore, shattered assumptions from the very beginning, showing that planetary systems are not limited to gentle environments like our solar system, but can thrive in the aftermath of destruction. The study of the Lich system has opened the door to new ways of thinking about not only planetary formation, but also the tools we use to detect planets. The extraordinary precision of pulsar timing made the discovery possible, and the fact that such sensitive measurements revealed not just one planet, but three, indicates that pulsar systems may hold more secrets than we currently realize. However, it remains strikingly rare to find such systems, which suggests that while the Lich system is real, it is also an outlier, a cosmic curiosity that defies the odds. Even so, its existence proves that the boundaries of possibility are far broader than anyone once thought. When astronomers first detected the planets of the Lich system, they didn't see them directly. Unlike the way we view Jupiter through a telescope or capture images of exoplanets today with advanced instruments, the discovery of Draugr, Poltergeist, and Phobiter came from something far subtler: the exact timing of the pulsar's radio pulses. Pulsars are nature's most precise clocks. Their beams sweep across space with astonishing regularity, sometimes with stability more accurate than the best atomic clocks on Earth. This predictability allows scientists to notice even the smallest deviations in timing, tiny irregularities that can hint at the presence of something unseen. Here's how it works. Imagine the pulsar as a cosmic metronome, clicking perfectly in rhythm. If the pulsar were truly isolated, those ticks, its radio pulses, would arrive at Earth in a steady, unchanging pattern. But if something massive is orbiting the pulsar, its gravity will tug on the star ever so slightly, causing it to wobble around a shared center of mass. As the pulsar shifts position during this orbital dance, the timing of its pulses changes. Sometimes the pulses arrive a little earlier than expected, and sometimes a little later. These variations are minuscule, measured in microseconds, but they are detectable with sensitive radio telescopes. By carefully analyzing these timing irregularities, astronomers can deduce the presence of orbiting planets, even if the planets themselves remain invisible. This technique, known as pulsar timing, is what led Alexander Wolszczan and Dale Frail to their groundbreaking discovery in 1992. Using the Arecibo Observatory in Puerto Rico, they collected precise measurements of the pulsar's emissions. At first, they noticed that the timing wasn't perfectly consistent. There were slight but repeating shifts. Rather than dismissing these as errors, they investigated further. What they found was extraordinary. The pattern of variations fit exactly with the gravitational influence of multiple orbiting bodies. The planets were pulling the pulsar just enough to alter the rhythm of its cosmic heartbeat, betraying their presence across the vastness of space. One of the most remarkable aspects of this detection method is its sensitivity. Pulsar timing is capable of revealing planets far smaller than those discovered by most other methods. While many exoplanet hunting techniques, like the transit method or radial velocity, are best suited for detecting large gas giants, pulsar timing can uncover planets as small as Earth, or even smaller. In fact, Draugr, the smallest of the Lich system's planets, is only about twice the mass of the Moon, yet its gravitational tug was strong enough to create detectable shifts in the pulsar's timing. This demonstrated that pulsar timing is among the most precise tools astronomers have ever developed for finding planets. Another powerful feature of pulsar timing is its ability to provide detailed information about planetary systems. By analyzing the exact timing variations, astronomers can calculate not only the presence of planets, but also their masses, orbital periods, and relative positions. In the case of the Lich system, this allowed scientists to piece together the structure of the planetary family without ever directly observing it. The stability of the orbits, the resonance between Poltergeist and Phobiter, and the existence of Draugr all became clear through the careful study of pulse arrival times. However, pulsar timing is not without challenges. The method requires incredibly precise observations over long periods, often years, to distinguish planetary signals from other sources of noise. Pulsars themselves can sometimes glitch, suddenly changing their rotation rate due to internal processes within the neutron star. Distinguishing between these natural variations and the gravitational effects of planets requires meticulous analysis. Yet, the success of Wolfskin and Frail proved that when done correctly, pulsar timing is one of the most powerful methods ever devised for detecting exoplanets. The implications of this were enormous. Not only did it confirm the first exoplanets in history, but it also established a method that could, in principle, detect even more planets in pulsar systems. While very few have been found since, suggesting that pulsar planets are rare, the technique remains a shining example of how creative observation can uncover the hidden structures of the universe. The pulsar's incredible precision gave astronomers a way to hear the tug of unseen worlds, showing that planets can betray themselves not by light or shadow, but by the faintest irregularities in a dead star's rhythm. The elegance of pulsar timing lies in this paradox. A star that should have been a graveyard, emitting nothing but deadly beams of radiation, instead became the perfect laboratory for discovering new worlds. The discovery method itself became part of the wonder, for it highlighted not just the existence of the planets, but also the ingenuity of science in uncovering them. And yet, even as astronomers celebrated this achievement, one question loomed large. Why should such planets exist at all? After all, the very event that created the pulsar, the supernova explosion, should have obliterated or ejected any nearby worlds. Their survival, or rebirth, remains one of the greatest puzzles in astrophysics. When astronomers first realized that planets were circling the Lich system, their immediate reaction was disbelief. Not because the data was unclear, but because everything we know about stellar death screams that planets should not have survived there. A pulsar is born in one of the most destructive events in the universe, a supernova explosion. To appreciate just how hostile this process is, imagine a massive star at the end of its life. For millions of years, it fuses hydrogen into helium, helium into heavier elements, and so on, until it builds up a dense iron core. At this point, the star can no longer sustain nuclear fusion, the process that balances gravity by producing outward pressure. Without that stabilizing force, the core collapses in an instant. Gravity wins, and the star's heart is crushed to unimaginable densities in less than a second. This collapse triggers a chain of destruction. The star's outer layers, unable to resist the shock of the core's implosion, rebound, and are blasted outward in a titanic explosion. Shockwaves ripple through the star at speeds of thousands of kilometers per second, tearing apart its structure and hurling material into space. The energy released in a single supernova can briefly outshine an entire galaxy of billions of stars. The radiation produced is staggering. X-rays, gamma rays, and neutrinos flood the surrounding space in amounts that dwarf anything produced by a living star. Any planets that once orbited nearby are caught in a maelstrom of unimaginable violence. The first destructive force is sheer heat and radiation. As the star detonates, its surroundings are bathed in an inferno capable of vaporizing entire worlds. Atmospheres would be the first to go, blown away by radiation pressure and searing winds. Oceans, if any existed, would be boiled into vapor and stripped into space. Even the surfaces of rocky planets would be scorched, melted, or atomized under the blast of energy. For gas giants, the outer layers would be torn away, leaving cores bare or obliterated. No protective shield, no magnetic field, no thick atmosphere could realistically withstand such an onslaught at close distances. The second destructive force is mechanical. The blast of debris hurled outward by the supernova moves with such velocity and density that it would tear through any planets in its path. Imagine fragments of stellar matter, hot gas, heavy elements, shock-heated plasma, slamming into worlds at speeds greater than anything in our solar system. Planets could be cratered beyond recognition, shattered entirely, or even blasted apart. In many cases, the gravitational stability of the system would be destroyed, with planets flung into interstellar space as rogue wanderers, rather than remaining bound to the collapsing remnant. The third destructive force is gravitational collapse. When the star's core shrinks into a neutron star, its gravity intensifies dramatically. The sudden redistribution of mass destabilizes the orbits of any nearby planets. Some would spiral inward and be torn apart by tidal forces, shredded into disks of debris that might later rain onto the neutron star. Others would be flung outward on chaotic, unstable trajectories. Stable orbits, the foundation of planetary systems, should not survive this kind of upheaval. And yet, in the Lich system, planets clearly did survive, or at least exist after the supernova. This is what makes them so baffling. By every calculation, the combination of shockwaves, radiation, and gravitational chaos should have destroyed any pre-existing planetary system. It should have left only a lonely neutron star spinning in the void. Instead, we see a family of rocky worlds maintaining delicate orbital resonances, circling in apparent defiance of the physics that should have annihilated them. This contradiction lies at the heart of the mystery. If the planets of the Lich system survived, how did they withstand such unimaginable destruction? Were they somehow far enough away to avoid being vaporized, later migrating closer to the Pulsar? Or were they obliterated and then replaced by new planets formed from the wreckage of the star? Neither explanation sits comfortably with current models of planetary science. Survival seems unlikely. Rebirth seems improbable. And yet, the planets are undeniably there, forcing astronomers to grapple with the uncomfortable truth that the rules of planet formation and survival are not as rigid as once thought. The Lich system, therefore, is more than just a collection of strange worlds. It is a cosmic paradox. Its planets occupy a space where logic says none should exist, a reminder that the universe often defies human expectations. To resolve this puzzle, scientists have turned to new theories, proposing that perhaps planets can be born even after a star's death, formed not in the cradle of a young stellar nursery, but in the aftermath of destruction. This leads us to one of the most intriguing possibilities of all, that pulsar planets are not survivors, but children of catastrophe, born from the very debris of the star's violent end. The paradox of the Lich system forced astronomers to ask a bold question. If planets shouldn't have survived the cataclysm of a supernova, could they have been born afterwards? This led to the most widely accepted explanation for their existence, the formation after death scenario. In this theory, the planets orbiting the pulsar are not ancient survivors from before the star's collapse, but new worlds forged in the chaos that followed. Far from being obliterated remnants, they are children of destruction, sculpted from the very ashes of their parent star. When a massive star explodes as a supernova, not all of its matter escapes into interstellar space. Some of it, slowed by gravity or deflected by the violence of the explosion, falls back toward the newly formed neutron star. This fallback material doesn't simply vanish. Instead, it can settle into a rotating disk of gas and debris around the pulsar. Astronomers call this a fallback disk, and it may resemble, in some ways, the protoplanetary disks that form around young stars. The difference is that instead of being made of cool primordial dust from a molecular cloud, this disk is made of enriched material forged in the supernova. Elements like carbon, oxygen, silicon, iron, and heavier metals blasted outward during the collapse. Over time, the disk cools and spreads out, creating a stable environment where matter can begin to clump together. Just as planets in our solar system grew from dust and rock colliding and sticking together in the sun's protoplanetary disk, pulsar planets may form from this fallback material. The process is messy and violent at first, but gravity has a way of organizing chaos. Small clumps merge into larger bodies, collisions form planetesimals, and eventually, full-fledged planets emerge. What's astonishing is that this process may happen relatively quickly on cosmic timescales, within tens of millions of years after the supernova, a blink of an eye compared to the billions of years over which planetary systems normally evolve. This theory neatly explains why the Lich system contains rocky, Earth-mass planets rather than gas giants. A fallback disk does not have the same vast reservoirs of hydrogen and helium that are present in young stellar nurseries. Instead, it is rich in heavier elements, the building blocks of terrestrial planets. This would naturally lead to small rocky worlds like Draugr, Poltergeist, and Phobetor, rather than giant gaseous planets like Jupiter or Saturn. It also accounts for why these planets orbit so close to the pulsar. Material in the fallback disk would settle into orbits near the neutron star, where it could gradually accumulate into planets. There's another fascinating twist. Planets born from fallback disks would be made of material fundamentally different from the planets in normal star systems. Because the supernova creates heavy elements in abundance, pulsar planets may be unusually metal-rich, potentially with higher densities than Earth. Some models even suggest the possibility of exotic worlds, planets with surfaces rich in carbon that could form crystalline structures or even massive diamond-like interiors. While this remains speculative, it underscores just how strange and alien pulsar planets could be compared to anything in the solar system. The fallback disk theory also helps resolve the puzzle of orbital stability. If the planets had survived the explosion intact, their orbits would likely have been chaotic, destabilized by the loss of the star's mass and the violence of the blast. But if they formed afterwards, their orbits would naturally settle into stable configurations as they accreted from the disk. This explains the delicate resonances observed between Poltergeist and Phobetor, gravitational dances that suggest they grew together from the same structured disk rather than being survivors thrown into disarray. Still, the theory is not without its challenges. For one, fallback disks around pulsars are rarely observed. They are faint, and detecting them requires sensitivity far beyond most current instruments. Additionally, not every pulsar shows evidence of planets, even though fallback material should, in theory, be common. This suggests that while possible, planet formation after death may require very specific conditions, the right amount of fallback mass, a stable disk, and enough time for cooling and accretion to occur. These circumstances may be so rare that only a handful of pulsar systems ever form planets, which explains why the Lich system remains such an extraordinary outlier among exoplanet discoveries. Nevertheless, the formation after death hypothesis paints a hauntingly poetic picture. It suggests that destruction and creation are intertwined in the universe, that even in the wake of stellar annihilation, new worlds can be born. The planets of the Lich system are not survivors clinging to existence. They are rebirths, sculpted from the wreckage of a dead star, proof that the cosmos has a way of recycling its chaos into new and unexpected forms. For astronomers, this idea transforms pulsar planets from anomalies into symbols of cosmic resilience. They are not impossible after all, but rather improbable products of one of the universe's most violent processes. And yet, not everyone agrees that pulsar planets must be newly born. Some scientists propose an alternate path. Perhaps they are survivors from another system altogether, captured long after the supernova's fury had subsided. This raises an even stranger possibility, that these planets did not simply form from the debris of death, but migrated from elsewhere, pulled into orbit around the pulsar by gravity's relentless hand. The fallback disk theory elegantly explains how new planets could arise from the ashes of a supernova, but it isn't the only explanation scientists have considered. Another possibility is that pulsar planets were not born after death at all, but rather are interstellar wanderers, worlds that once belonged to other systems and were later captured by the pulsar's immense gravity. This captured planet hypothesis suggests that Draugr, Poltergeist, and Phobetor may not be children of the pulsar, but cosmic refugees, survivors from elsewhere that somehow found themselves bound to an undead star. The idea of planetary capture is not far-fetched. Gravity is universal and merciless, and under the right circumstances, it can seize objects drifting through space and lock them into orbit. Our own solar system may hold evidence of this process. Some astronomers believe that certain irregular moons of the giant planets, like Neptune's Triton, were captured objects rather than bodies that formed in place. If a pulsar were to pass near another planetary system, or if free-floating rogue planets happened to wander into its gravitational well, it is theoretically possible that they could become trapped in orbit around it. For pulsars, the conditions for capture are extreme. Unlike stars that still shine brightly, pulsars are small, compact, and extraordinarily dense, meaning their gravitational pull is concentrated into a tiny volume. This makes them incredibly effective at tugging on passing objects. If a planet or a small planetary system passed close enough, the pulsar could strip it away from its original star and claim it as its own. Over time, such captured planets might settle into stable orbits, even forming multi-planet arrangements like those seen in the Lich system. One of the strengths of the capture hypothesis is that it helps explain the apparent rarity of pulsar planets. If they formed naturally from fallback disks, we might expect to see them more frequently, since supernovae are common throughout the galaxy. But if they are captured, then their existence depends on chance encounters between pulsars and planetary systems, or rogue planets, an event astronomers would expect to be exceptionally rare. This would fit with the fact that out of thousands of exoplanets discovered, only a tiny handful orbit pulsars. The capture theory also provides a possible explanation for why the planets in the Lich system are relatively close to their host star. Captured objects, when pulled in by strong gravity, may lose orbital energy through gravitational interactions or collisions with debris, eventually spiraling inward until they stabilize in tight orbits. This process could account for why Draugr, Poltergeist, and Phobiter orbit at distances similar to the inner planets of our solar system, rather than farther out. However, there are difficulties with the capture scenario. Capturing a planet into orbit is not simple. It requires precise conditions. Usually, an object passing near a massive body simply swings past and continues on its way, unless some mechanism allows energy to be dissipated. For example, in a binary system, capture can happen when one object steals orbital energy from another. But pulsars are often solitary, and without a companion star or significant debris disk, the mechanism for energy loss becomes harder to explain. The planets of the Lich system not only orbit the pulsar, but also exhibit stable, resonant orbits with each other, suggesting they share a common origin. Such coordination is difficult to reconcile with random captures, which would likely lead to chaotic orbital arrangements rather than the harmonious system we observe. Still, the possibility of capture remains compelling because it acknowledges the sheer unpredictability of cosmic dynamics. Rogue planets are thought to be incredibly common in the galaxy, perhaps even outnumbering stars. If that is true, then pulsars may occasionally ensnare one of these nomadic worlds, producing rare but fascinating planetary systems. In this sense, the Lich system could be a showcase of cosmic serendipity, worlds that once drifted alone in the dark, only to be claimed by the gravity of a dead star and locked into its orbit for billions of years. Whether the planets of the Lich system are born from fallback material or captured survivors, both scenarios emphasize just how improbable their existence is. They force astronomers to widen their perspective on planetary formation and survival, showing that there may be many different pathways for planets to end up in extraordinary circumstances. Yet even if they were born or captured, another question remains. How have these planets managed to withstand the relentless radiation and particle storms unleashed by their host star? By all accounts, they should have been stripped bare or destroyed long ago. The answer to this deepens the mystery even further. One of the greatest puzzles surrounding the Lich system is not simply how its planets came to be, but how they have managed to endure the relentless radiation of their host. A pulsar is not a quiet star. It is a cosmic engine of violence. With each rotation, it hurls beams of electromagnetic energy across space, blasting anything in their path with X-rays, gamma rays, and torrents of charged particles. These emissions are among the most destructive forces in the universe. For any nearby planet, this is an environment of constant bombardment, an invisible rain of death that should strip away atmospheres, scorch surfaces, and erode planetary material over time. Yet, Draugr, Poltergeist, and Phobiter still remain, circling the pulsar in stable orbits as though immune to the very conditions that should obliterate them. How can this be? To understand the severity of the problem, we need to consider the raw power of pulsar radiation. Gamma rays are the most energetic form of light, capable of penetrating deep into matter and breaking apart atomic bonds. X-rays, while slightly less energetic, are still powerful enough to ionize atoms, blasting electrons from their shells and creating highly reactive particles. On Earth, we are shielded from most cosmic radiation by our magnetic fields and thick atmosphere, but in the vicinity of a pulsar, those defenses would be shredded almost instantly. Over time, this constant exposure should strip any planet bare, leaving nothing but lifeless, irradiated rocks. If the planets of the Lich system had atmospheres in the past, they would have long since been blasted into space. Even oceans or subsurface reservoirs of water would be vaporized by the unyielding onslaught. And yet, the planets endure. Their rocky structures remain intact, their orbits stable, and their presence undeniable. This presents one of the strangest mysteries of pulsar planets. How can matter withstand conditions that should, by every calculation, grind it down to dust? One possibility is that the planets are far denser and more resilient than normal terrestrial worlds, formed from the heavy elements of a supernova or captured survivors enriched with metals. They may be structurally stronger than Earth-like planets. This would not protect them from radiation stripping away atmospheres, but it could help them resist being eroded or broken apart by particle bombardment. In other words, they may survive not as habitable worlds, but as bare, hardened husks forged to withstand cosmic punishment. Another possibility is sheer endurance through scale. The Lich system's planets, particularly Poltergeist and Phobiter, are several times more massive than Earth. Larger rocky planets have stronger gravitational pulls, which means they can hold on to material more effectively. While radiation may strip gases and lighter elements from their surfaces, their gravity could still retain heavier elements, ensuring the planets remain solid. Draugr, being far smaller, is the most fragile, and it may represent the stripped-down core of a once larger planet or a fragment left behind after more extensive destruction. In this view, the planets are not untouched survivors, but scarred remnants, the stubborn cores that even a pulsar could not erase. Magnetic fields offer another intriguing possibility. On Earth, our magnetosphere shields us from the solar wind, deflecting charged particles that would otherwise bombard the atmosphere and surface. If the Lich system's planets once had or still maintained strong magnetic fields, they could offer some degree of protection against the pulsar's particle storms. However, whether such fields could endure for billions of years under constant assault is questionable. Magnetic fields are generated by the motion of molten metal in a planet's core, and the stability of such a system under pulsar conditions is uncertain. Yet, if these worlds are unusually metal-rich, as suggested by their possible supernova origins, they may generate stronger and longer-lasting fields than Earth. But even with gravity and magnetic fields, the sheer intensity of pulsar emissions raises doubts. Radiation resistance might ultimately come down to the fact that the planets are already stripped to their most basic forms. If they lost their atmospheres billions of years ago, and if any volatile materials like water or ice have long since been destroyed, what remains is a hardened rocky shell. Such bare planets would no longer be vulnerable to atmospheric erosion or surface vaporization. Instead, they would exist in a kind of stasis, battered but unbroken, circling their host star as barren relics of cosmic endurance. Their survival does not mean they are thriving, but rather that they are reduced to their most indestructible essence. Some scientists have gone further, suggesting that the unique conditions of pulsar environments may produce exotic planetary compositions. For instance, if these planets contain unusually high amounts of carbon, immense pressure within their interiors could create diamond-rich structures. A diamond planet would be extraordinarily resistant to erosion, able to withstand radiation and particle impacts far better than ordinary rock. While speculative, this idea highlights just how unusual pulsar planets may be, potentially constructed of materials that are far stronger than those found on Earth or Mars. It is also worth noting that pulsar emissions, while deadly, are highly directional. The beams sweep through space like lighthouses, and their impact depends on whether a planet lies directly in their path. If a planet orbits in a zone where the beams do not constantly strike, it may receive less radiation than expected, allowing it to survive longer. However, given the tight orbits of the Lich system's planets, it is hard to imagine they completely avoid exposure. More likely, they are enduring despite the constant bombardment, a testament to their durability. Ultimately, the mystery of radiation resistance underscores the resilience of matter in extreme environments. The planets of the Lich system are not lush worlds with protective atmospheres and oceans, but scorched survivors, or perhaps rebirths, that persist as silent, hardened stones orbiting a star that should have destroyed them. Their existence suggests that even in places of unimaginable hostility, nature finds ways to preserve structure, if not habitability. These planets are monuments to endurance, cosmic ruins that should have been erased yet continue to circle defiantly in the darkness. This resilience deepens the enigma of pulsar planets. They should have been vaporized by the supernova that birthed the pulsar, stripped bare by radiation and destabilized by gravitational collapse. Yet they remain. Understanding how they endure pushes us to consider not just survival, but the possibility that their very composition is unusual, perhaps denser, stronger, or stranger than normal rocky planets. This mystery leads directly into another puzzle, the question of density. Are pulsar planets simply ordinary rocky worlds that happen to have survived? Or are they built from exotic materials that defy our expectations entirely? The survival of planets in the Lich system already seems improbable. But when astronomers looked deeper into their properties, another mystery emerged: their density. At first glance, Draugr, Poltergeist, and Phobiter appear to be rocky planets, somewhat similar in mass and size to Earth. They orbit stably, they tug on the pulsar in predictable ways, and their presence is unmistakable. Yet, when scientists began to model their possible compositions, questions arose about whether these planets are truly normal rocky worlds or something far stranger. Some theories suggest they may even be ultra-dense objects, potentially composed of exotic matter unlike anything found in our solar system. The standard assumption is that pulsar planets should be rocky. This makes sense if they formed from fallback material after the supernova. A supernova produces heavy elements like iron, carbon, and silicon in vast quantities, and these would dominate any disk of debris left behind. Unlike the hydrogen and helium-rich environments that form gas giants around young stars, a pulsar's disk would favor small, dense, terrestrial-type planets. This explanation aligns well with the observed sizes and masses of Poltergeist and Phobiter, which fall into the Earth mass range. Draugr, being only about twice the mass of the Moon, also fits comfortably into this rocky picture. But the density puzzle arises because of the extraordinary environment these planets inhabit. A pulsar's radiation and particle bombardment should, over billions of years, gradually strip away lighter materials. Volatiles like water, carbon dioxide, and even lighter silicates could be eroded, leaving behind planets enriched in metals and heavier elements. If this is the case, the Lich system's planets may be far denser than Earth. Not ordinary rocky worlds, but iron-rich survivors, cores stripped bare by the pulsar's relentless energy. They could resemble the metallic core of Mercury, but on a much larger scale. Such planets would be incredibly heavy for their size, with higher densities than typical terrestrial bodies. Some models push this even further, suggesting the possibility of exotic matter. Neutron stars themselves are composed of materials so dense that a teaspoon would weigh billions of tons. While planets could never reach such extremes, some theorists speculate that small fragments of neutron-rich material might escape during the supernova and become incorporated into nearby planets. If so, the planets of the Lich system could contain patches of ultra-dense matter, giving them properties unlike anything seen in ordinary planetary science. Though highly speculative, this raises the possibility that pulsar planets are not just survivors or rebirths, but unique laboratories of exotic physics. One particularly intriguing idea is the existence of carbon planets, or even diamond planets, formed from supernova debris. A supernova produces abundant carbon, and under immense pressure within a planet's interior, carbon can crystallize into diamond. If the Lich system's planets contain vast amounts of carbon, they might be crystalline worlds, giant, diamond-rich spheres orbiting a star that itself is a remnant of destruction. While such ideas may sound more like science fiction, they are supported by the known chemistry of stellar explosions and the extreme pressures planets can generate internally. A diamond world would also explain the unusual resilience of these planets, as diamond is one of the hardest substances known, capable of withstanding erosion better than silicate rock. Another possibility is that these planets are unusually enriched in heavy metals like iron and nickel, giving them super dense compositions similar to giant planetary cores. Their densities could be 2 to 3 times that of Earth, making them not only resilient against radiation, but also gravitationally more robust. Such planets might even retain small amounts of atmosphere, clinging tightly to whatever gases remain, though the chances of habitability would still be virtually zero. What makes the density puzzle so compelling is that we currently lack direct measurements of these planets' compositions. Pulsar timing reveals their masses and orbital properties but cannot tell us exactly what they are made of. This leaves a wide range of possibilities open, from stripped-down rocky husks to bizarre exotic matter hybrids. Future telescopes may one day provide more clues by detecting faint signatures of debris, dust, or secondary effects from the planets, but for now, their true nature remains uncertain. The density mystery also has broader implications for planetary science. If pulsar planets are indeed ultra-dense, they represent a new category of world that challenges our understanding of what planets can be. They would show that planets are not limited to the familiar rocky, gaseous, and icy categories of our solar system, but can include strange, hyperdense survivors born from stellar death. If, on the other hand, they are simply ordinary rocky planets that happen to endure extraordinary conditions, their survival alone forces us to reconsider the durability of planetary structures. Either way, the Lich system's planets expand the boundaries of possibility. As astronomers continue to study them, the density puzzle underscores a larger truth. Pulsar planets are not anomalies to be brushed aside, but vital keys to understanding how matter behaves under extremes. They could be rocky survivors, metal-rich relics, or even exotic, diamond-like creations forged from supernova debris. Whatever they are, their existence compels us to look beyond the ordinary categories of planets and accept that the cosmos may harbor worlds stranger than we have ever imagined. And the Lich system is not alone. Though rare, other pulsar planet systems have been found, and they add new layers of complexity to the puzzle. If the Lich planets pose questions about survival and density, other pulsar systems reveal even more bizarre circumstances, such as planets orbiting not just pulsars, but pulsars paired with other stellar remnants, like white dwarfs. These discoveries suggest that pulsar planets may not be isolated oddities, but glimpses into a broader, though rare, phenomenon. The Lich system may be the most famous pulsar planetary system, but it is not the only one. While planets around pulsars are exceedingly rare, each discovery adds a new layer of intrigue to the mystery of how such worlds can exist in the first place. Perhaps the most remarkable case outside of the Lich system is PSR B1620-26E, a planet with an extraordinary nickname, the Methuselah planet. Named after the biblical figure who lived nearly 1,000 years, this planet is considered one of the oldest known in the entire universe, an ancient survivor orbiting not just one stellar remnant, but 2. Its existence is a story of survival, endurance, and cosmic strangeness that stretches back nearly to the dawn of time. Located about 12,400 light-years away in the globular cluster M4, the Methuselah planet is thought to be around 12.7 billion years old. To put that into perspective, our solar system is only about 4.6 billion years old, and the universe itself is about 13.8 billion years old. That means this planet formed when the universe was less than 1 billion years old, at a time when galaxies were still in their infancy and heavy elements were far more scarce than they are today. The mere fact that a planet could form in such a young, chemically primitive universe is astonishing, as planet formation requires heavy elements like carbon, silicon, and iron, materials that had only just begun to be produced by the earliest generations of stars. What makes PSR B1620-26B even stranger is the company it keeps. Unlike the Lich system, where planets orbit a lone pulsar, the Methuselah planet orbits a binary system composed of a pulsar and a white dwarf. This pairing is itself unusual. A pulsar, born from a supernova, and a white dwarf, the fading core of a less massive star, locked together in orbit. The planet circles this pair at a distance about twice as far as Uranus is from the Sun, on a wide, stable orbit that has endured for billions of years. Its survival amid such a chaotic stellar environment is almost unfathomable. The Methuselah planet is estimated to be about 2.5 times the mass of Jupiter, making it a giant compared to the smaller, rocky worlds of the Lich system. Its size and composition suggest it formed in a more traditional way, like the gas giants in our solar system, before being incorporated into the binary system. The big question, however, is how it ended up where it is now. One possibility is that the planet originally formed around one of the stars in the system, only to be captured into its current orbit after those stars evolved into a pulsar and a white dwarf. Another idea is that the planet was once part of a completely different system, but was pulled in during a close encounter in the dense stellar environment of the globular cluster. Globular clusters are known for their crowded conditions, with stars packed together far more tightly than in the relatively open spaces of the galactic disk where our Sun resides. This density makes gravitational interactions between stars far more common. In such an environment, it is plausible that the Methuselah planet was tossed around like a cosmic pinball, ejected from one orbit and captured into another. That it has remained in a stable configuration for billions of years, orbiting a pulsar white dwarf binary, is nothing short of miraculous. The Methuselah planet stands in stark contrast to the Lich system. While Draugr, Poltergeist, and Phobodor are rocky, Earth-mass planets orbiting close to their pulsar, PSR B 1620-26b is a massive gas giant orbiting at a great distance from its hosts. The Lich system may represent planets born from fallback material or tightly bound survivors, while the Methuselah planet seems more like a captured wanderer, a planet formed early in cosmic history, tossed about by stellar encounters, and eventually settling into an orbit around two dead stars. Together, these examples show just how diverse pulsar planets can be, defying neat categories or simple explanations. What both systems highlight is the resilience of planets under conditions that should not favor survival. The Lich planets orbit close to deadly radiation, yet remain intact. The Methuselah planet exists in one of the densest and most chaotic regions of the galaxy, orbiting stellar remnants that should have destabilized it long ago, yet it persists after more than 12 billion years. These examples suggest that while pulsar planets are rare, they are also powerful reminders that planetary systems can endure in forms and places we once thought impossible. The Methuselah planet, with its nearly incomprehensible age, also reshapes our perspective on planetary history. It shows that planets have existed nearly as long as stars themselves, meaning that worlds were forming across the universe billions of years before Earth came into being. While life is unlikely in such hostile environments, the sheer antiquity of such planets suggests that planetary formation is not a recent or fragile phenomenon. It is a fundamental process of the cosmos, capable of producing worlds that last almost as long as the universe itself. Yet, if pulsar planets can be as varied as small rocky bodies and ancient gas giants orbiting stellar corpses, the next question is whether these worlds are dynamically stable. After all, pulsars are born from explosions that disrupt gravitational harmony, and binary systems add layers of complexity. How can planets orbiting such chaotic remnants maintain stability over billions of years? The answer lies in a delicate balance of orbital mechanics, where even the slightest misalignment could spell doom. But somehow these worlds have found equilibrium. The presence of pulsar planets is already baffling enough, but what makes them even stranger is the fact that many of them seem to orbit with remarkable stability. On the surface, this seems almost impossible. Pulsars are born in supernova explosions that unleash titanic shockwaves, gravitational upheaval, and radiation capable of sterilizing entire star systems. Such an event should destabilize orbits, scatter planets into interstellar space, or smash them into debris. And yet, in systems like the Lich, Draugr, Poltergeist, and Phobodor maintain finely tuned orbital patterns that have lasted for billions of years. This paradox, how planets can remain stable in the aftermath of cosmic chaos, has become one of the most fascinating puzzles in pulsar planet research. To appreciate the improbability of stability, consider what happens during a supernova. The collapsing star loses a significant portion of its mass in a matter of seconds, blasting it outward into space. When this happens, the gravitational balance of the system is shattered. Planets that once orbited under the influence of the star's original mass suddenly find themselves with less gravity holding them in place. Typically, this results in chaos. Some planets may spiral inward and be consumed, while others are flung outward into space as rogue worlds. In theory, very few stable orbits should survive this process, and yet, pulsar planets clearly do, forcing scientists to question why. One explanation is that stability arises not from survival through the explosion, but from reformation after the chaos. If planets like those in the Lich system formed from fallback disks after the supernova, they would naturally emerge into stable orbits because they coalesced from the same rotating disk of material. Much like planets in our solar system formed from the sun's protoplanetary disk, these pulsar planets may have developed in a balanced, organized system of their own. The resonant orbits of Poltergeist and Phobovitor, in which they gravitationally influence each other in predictable cycles, strongly support this idea. Their resonance is no accident. It suggests a shared formation history that led to long-term orbital harmony. But in cases like the Methuselah planet, which almost certainly did not form from a fallback disk, the explanation must be different. PSR B 1620-26b orbits a binary system containing both a pulsar and a white dwarf. Such an arrangement should be dynamically unstable, especially given the crowded environment of a globular cluster where stellar encounters are frequent. Yet, Methuselah has circled its hosts for billions of years without being ejected or destroyed. Astronomers believe this is due to the delicate balance of distances involved. The planet orbits the binary pair at a wide separation, far enough away that the violent gravitational interactions of the inner system do not disturb it significantly. In orbital mechanics, this is known as a hierarchical system, where one set of objects, the pulsar and white dwarf, orbit closely, while another object, the planet, orbits much farther out, maintaining stability. Even in the Lich system, the stability is delicate. The orbits of Draugr, Poltergeist, and Phobovitor are tightly interwoven, with subtle gravitational interactions influencing their timing. These interactions are not destructive, but cooperative, creating a resonant chain that locks the planets into predictable rhythms. Without such resonances, their orbits might eventually decay into instability. It is a testament to the resilience of orbital mechanics that even in the aftermath of a supernova, gravity can sculpt order out of chaos, preserving planetary motion across billions of years. Still, astronomers caution that pulsar planets are balanced on a knife's edge. Even tiny disturbances, whether from additional debris, passing stars, or shifts in the pulsar itself, could destabilize them over long timescales. Their stability is not absolute, but relative. They endure because the conditions allow them to, but their environment remains hostile. Unlike the solar system, where planets enjoy relative peace, pulsar systems are arenas of violence where survival is tenuous. This is why pulsar planets are described as being both stable, yet unstable. Their orbits can endure for billions of years, but the margin for error is razor thin, and the forces threatening them are immense. This paradox highlights a broader truth about the universe. Order can emerge from chaos, but it is fragile. Pulsar planets demonstrate that even in the wake of stellar destruction, gravitational dynamics can conspire to create enduring systems. Whether formed anew from fallback disks or captured and shepherded into stability, these worlds embody a delicate balance that defies intuition. Their very survival suggests that planetary stability is not as rare as we once thought, even in extreme environments. Yet, stability does not mean uniformity. The diversity of pulsar planets extends not only to their orbital arrangements, but also to their physical characteristics. While some are tiny, moon-sized fragments, others rival or exceed Earth in mass. This wide range of sizes and masses underscores just how unpredictable these systems can be, and it leads naturally to the next question. What is the size and mass range of pulsar planets, and what does this tell us about their origins? One of the most surprising aspects of pulsar planets is their diversity in size and mass. When astronomers first confirmed the planets around the Lich system, they realized that these worlds did not fall neatly into a single category. Instead, they represented a spectrum, ranging from a small, moon-like fragment to multiple Earth mass bodies orbiting a dead star. This range immediately set pulsar planets apart from the early expectations of exoplanet hunters, who had assumed that the first planets detected outside our solar system would likely be massive, Jupiter-sized worlds. Instead, pulsar planets revealed something far stranger. Even in the aftermath of stellar death, planetary systems could produce or sustain bodies of vastly different scales. Take Draugr, the smallest of the Lich system's planets. At only about twice the mass of the Moon, it is the lightest exoplanet ever detected by pulsar timing. Its existence alone is remarkable because it demonstrates the extraordinary sensitivity of pulsar timing as a detection method. Detecting something so small orbiting thousands of light years away would have been nearly impossible with most other exoplanet techniques, but the precision of the pulsar's rhythmic beams allowed astronomers to spot it. Draugr may represent the stripped-down core of a once larger planet, or a fragment of matter that coalesced from the pulsar's debris disk. Either way, its survival in such a hostile environment highlights just how broad the spectrum of pulsar planets can be. Moving up in size, we find Poltergeist and Phobiter, both of which are several times more massive than Earth. These planets, orbiting farther out than Draugr, show that pulsar systems are not limited to tiny fragments of rock, but can host full-fledged terrestrial planets. Their masses suggest that they formed from large amounts of fallback material after the supernova, or that they were captured intact from elsewhere. Their presence alongside a smaller body like Draugr in the same system is particularly intriguing because it implies that the processes forming or capturing these worlds can yield a wide range of outcomes, not just uniformity. The diversity within a single system underscores that pulsar planet formation is a messy, unpredictable business. Beyond the Lich system, the Methuselah planet, PSR B1620-26b, shows the other extreme of the size spectrum. This massive gas giant is roughly 2.5 times the mass of Jupiter, dwarfing the Earth-sized worlds of the Lich system. Its existence demonstrates that pulsar planets are not restricted to rocky survivors or fragments, but can include enormous giants as well. While the Lich planets likely represent fallback worlds forged from supernova debris, the Methuselah planet almost certainly formed in a more conventional environment before being captured or surviving long enough to orbit a pulsar white dwarf binary. This contrast illustrates that pulsar planets can appear in radically different forms, depending on their origins and the unique histories of their systems. What is striking about this range is not only the diversity of sizes, but also the fact that such planets can remain stable in such extreme conditions. Tiny bodies like Draugr should, in theory, be the most vulnerable to radiation and particle stripping, yet it persists. On the other hand, massive worlds like the Methuselah planet show that gas giants, too, can find homes around pulsars under the right conditions. This wide range of planetary sizes challenges simple explanations and makes it clear that pulsar planets are not just one kind of anomaly, but a category of anomalies, each with its own story. The diversity also provides clues about how these planets may form. Small, moon-like bodies suggest accretion from thin debris disks, where only limited material was available. Earth-mass planets imply more substantial fallback material or stable, longer-lived disks that allowed for larger planets to develop. Gas giants like Methuselah point towards survival or capture scenarios where pre-existing planets from before the supernova managed to endure or were pulled into orbit after the fact. By studying the size and mass range of pulsar planets, astronomers gain insights into the multiple pathways by which these strange systems may come to exist. But there's a catch. While pulsar planets can span a wide range of masses, their environments make it highly unlikely that any of them retain atmospheres. The intense radiation of their hosts would strip gases away over time, leaving even the largest planets barren and exposed. This means that while pulsar planets may range in size from tiny rocky husks to giant gas worlds, their surfaces and atmospheres, or lack thereof, are likely far more uniform. They are, in almost every case, scorched, lifeless relics. This realization brings us to another critical question. What happens to atmospheres in the presence of a pulsar, and can any of them survive under such conditions? One of the most haunting truths about pulsar planets is that, no matter their mass or size, they almost certainly orbit as bare, airless husks. For all the intrigue surrounding their origins, densities, and orbital stability, the question of atmospheres, or rather the lack of them, remains one of the most important in understanding what these worlds are really like. In nearly every model and theory, scientists conclude that pulsar planets are stripped to their rocky cores, unable to maintain the protective gaseous layers that make planets like Earth habitable. The reason lies in the sheer brutality of the radiation environment created by their host stars. A pulsar is not a gentle source of light and warmth like the sun. Instead, it is a machine of destruction, blasting X-rays, gamma rays, and high-energy particles into its surroundings with incredible intensity. For any planet orbiting within reach of these emissions, the consequences are devastating. Atmospheric molecules are constantly bombarded by this radiation, broken apart in a process called ionization. As atoms and molecules are stripped of electrons, they gain enough energy to escape the planet's gravity and are blown into space. This process, known as atmospheric escape, happens even in less extreme conditions. Our own Earth steadily loses hydrogen and helium from its upper atmosphere, though at rates so slow that they pose no danger. Around a pulsar, however, the process would occur on a catastrophic scale, quickly removing all but the densest of gases. The stripping is further accelerated by the pulsar's particle winds. These are streams of high-energy particles, often traveling at nearly the speed of light, that slam into any nearby worlds. On Earth, our magnetosphere and atmosphere shield us from much of the sun's particle wind, but even then, strong solar storms can cause temporary disruptions like auroras and damage to satellites. For a pulsar planet, no such protection is adequate. The pulsar wind is billions of times stronger than anything the sun produces, a constant hurricane of charged particles tearing into any atmosphere with overwhelming force. Over time, the atmosphere would be stripped away layer by layer until nothing remains. Scientists believe that this fate would be nearly universal for pulsar planets. Whether a planet starts with a thin Earth-like atmosphere or a thick Venus-like blanket, the result is the same: total loss. Even massive gas giants like the Methuselah planet are not immune. While their deeper atmospheres might survive longer than a thin terrestrial envelope, the outer layers would still be eroded, leaving behind altered, possibly diminished giants. In the extreme case of smaller rocky planets like Draugr, atmospheric survival is virtually impossible. Their weaker gravity would be no match for the pulsar's ferocity, ensuring they orbit as airless rocks. Another important factor is time. Pulsars remain active for billions of years, continuously emitting radiation and particle winds. Even if a pulsar planet somehow managed to hold on to an atmosphere initially, it would not endure for long. Within a few million years, an eye blink on cosmic timescales, most or all of its gaseous layers would be stripped away. This means that by the time we observe pulsar planets today, long after their formation, they have had billions of years to be eroded by radiation. It is not just likely but inevitable that they exist now as barren worlds with no atmospheric shielding. The consequences of losing an atmosphere extend far beyond the absence of breathable air. Atmospheres play critical roles in regulating surface temperatures, protecting against radiation, and enabling liquid water to exist. Without one, a planet's surface is exposed directly to the vacuum of space and the harsh rays of its star. Temperatures swing violently between extremes, with no insulating blanket to trap heat or distribute it evenly. Radiation bombards the surface without resistance, sterilizing it and erasing any chance of life as we know it. In short, the absence of atmospheres makes pulsar planets some of the most inhospitable environments in the universe. And yet, the absence of atmospheres is not just a story of destruction, it also tells us something important about the origins and compositions of these worlds. If pulsar planets truly formed from fallback disks after supernova explosions, they would have been composed largely of heavy elements like iron and carbon, not volatile gases. This means they may never have had thick atmospheres to begin with. Instead, they might have always been dense, rocky planets with only the thinnest gaseous coverings. In this case, the pulsar's radiation simply finished the job, ensuring that whatever trace gases they started with were swept away. There is, of course, a sliver of speculation about whether subsurface environments could still harbor volatiles. Even without atmospheres, planets might retain materials underground, shielded from the pulsar's radiation. Pockets of water ice, subsurface oceans, or buried gases could, in theory, exist in these hidden reservoirs. However, this remains speculative at best, as the intense heat and radiation of a pulsar would likely penetrate even beneath the surface over billions of years. For now, the prevailing consensus is clear. Pulsar planets are almost certainly barren rocks, stripped of atmospheres and incapable of supporting the conditions for habitability. This realization underscores why pulsar planets remain such profound scientific curiosities. They are not promising candidates for life or human exploration, but rather extreme examples of planetary endurance. Their lack of atmospheres is not a weakness, but a testament to their resilience. Stripped bare by the harshest forces in the cosmos, they remain as skeletal reminders that planets can persist even when reduced to their most fundamental forms. And yet, as bleak as this picture may seem, the question of habitability is not entirely dismissed. While pulsar planets likely lack atmospheres, some scientists have wondered whether life could still find refuge beneath their surfaces, shielded from radiation and extremes. This speculation leads naturally to one of the most intriguing debates about pulsar planets. Could they, against all odds, harbor any form of habitability in hidden refuges far below their irradiated shells? The idea of habitability on pulsar planets seems almost absurd at first glance. How could life possibly take hold in a system where the very star itself is a corpse, endlessly spewing lethal radiation into its surroundings? Without atmospheres, exposed to gamma rays and X-rays, and orbiting in the aftermath of one of the most catastrophic explosions in the universe, these worlds seem destined to remain barren rocks, stripped and lifeless. Yet, in the spirit of scientific curiosity, astronomers and astrobiologists have asked a provocative question. Is it possible, even in such extreme conditions, for life to find refuge? The debate begins with the recognition that surface life, as we understand it, is impossible on pulsar planets. With no protective atmosphere, radiation from the pulsar would sterilize the surface almost instantly. DNA or other complex molecules would be torn apart by high-energy particles before they could replicate, making surface habitability a non-starter. However, life does not necessarily need to exist on the surface. On Earth, we have discovered thriving ecosystems in some of the most inhospitable environments imaginable. Deep beneath the ocean floor, in caves shielded from sunlight, and near hydrothermal vents spewing toxic chemicals. These discoveries remind us that life is adaptable, and that habitability might sometimes be hidden underground. For pulsar planets, the possibility of habitability centers on subsurface refuges. If a planet retains enough internal heat from its formation or from radioactive decay in its interior, it could sustain underground reservoirs of liquid water or other solvents beneath a thick crust. Such water would be shielded from the pulsar's deadly radiation by kilometers of rock, creating a safe haven where conditions could be relatively stable. On Earth, subsurface life has been discovered kilometers below the surface, living off chemical reactions between water and rock. A similar process, called chemosynthesis, could in theory support microbial life on pulsar planets, even in the absence of sunlight. Some researchers speculate that if these planets formed from fallback material, they may contain abundant heavy elements and carbon-rich compounds. If subsurface water or liquid hydrocarbons exist, these materials could provide the chemistry needed for life. The idea becomes even more intriguing when we consider that supernovae seed their surroundings with a wide array of elements, including those essential for biology: carbon, oxygen, nitrogen, and iron. If a pulsar planet locked away these elements beneath its surface, it might, in principle, provide a chemical environment capable of supporting life, despite the lethal conditions above. The main challenge is whether such subsurface environments could persist for billions of years. Pulsar planets are ancient, and their radioactive heat sources would diminish over time. Without a thick insulating atmosphere, the surface would cool rapidly, potentially freezing subsurface water into solid ice. However, if these planets are large and dense enough, their interiors might retain heat for extraordinarily long periods, especially if tidal forces from their host star or neighboring planets contribute additional heating. In systems like the Lich, where orbital resonances link the planets in subtle gravitational interactions, tidal heating could provide a steady trickle of energy to keep underground reservoirs from freezing completely. Despite these possibilities, the consensus is that habitability on pulsar planets is extraordinarily unlikely. The challenges are immense. Relentless radiation, lack of atmospheres, and uncertain energy sources all conspire against the survival of life. Even if subsurface pockets of water or hydrocarbons exist, the conditions may be too unstable or too sterile to support ecosystems. But the fact that scientists even entertain the idea speaks to the broader lesson of pulsar planets. They constantly force us to expand our definitions of what is possible. What seems impossible at first glance may turn out to be merely improbable. The habitability debate also has profound implications for astrobiology. If life could, in principle, find refuge beneath the crust of a pulsar planet, then the potential range of habitable environments in the universe expands dramatically. It would mean that even the ruins of dead stars might harbor niches for biology, widening the scope of where we might one day search for life. On the other hand, if pulsar planets truly are sterile, they serve as reminders of the limits of habitability, illustrating the many ways in which planetary environments can fail to support life. Either way, they sharpen our understanding of what makes a planet capable, or incapable, of becoming a cradle for biology. This speculative discussion of habitability naturally leads to another protective mechanism worth considering: magnetospheres. On Earth, our magnetic field is essential for shielding us from the solar wind and preserving our atmosphere. Could strong planetary magnetic fields play a role in helping pulsar planets resist their hostile environments? Could magnetospheres, if powerful enough, make the difference between total atmospheric loss and the faint hope of preservation? The next step in the pulsar planet mystery lies in exploring this possibility. The idea of pulsar planets being able to maintain even the slightest shred of resilience in such an inhospitable environment inevitably leads to one of the most fascinating protective mechanisms in planetary science: the magnetosphere. On Earth, our magnetic field plays a vital role in shielding us from the constant assault of the solar wind. Without it, charged particles streaming from the sun would gradually erode our atmosphere, strip away gases critical to life, and expose the surface to dangerous levels of radiation. While the pulsar's environment is infinitely harsher than our sun's, it raises the question: could a powerful planetary magnetic field act as a kind of cosmic shield, allowing pulsar planets to resist the unrelenting storms of high-energy particles? To answer this, we first need to recall how magnetospheres work. A planet's magnetic field is usually generated by a dynamo effect in its core. This effect arises when molten, electrically conductive materials like liquid iron or nickel move and circulate due to heat and rotation. These flows generate electric currents, which in turn create magnetic fields. If the conditions are right, this process sustains a global magnetic shield that extends far into space, deflecting or trapping incoming charged particles. Earth's magnetosphere, for instance, forms a vast protective bubble that channels solar particles away, only allowing some to interact near the poles, where they create the auroras. Now, imagine a planet orbiting a pulsar. The conditions here are much more extreme than those experienced by Earth. Instead of a gentle solar wind, the planet faces a storm of ultra-relativistic particles, accelerated to near the speed of light by the pulsar's intense magnetic field. The flux of these particles is so high that without protection, they would slam into the planet's atmosphere and surface continuously, eroding matter and sterilizing everything in their path. For a pulsar planet to stand even the faintest chance of resisting this onslaught, its magnetosphere would need to be unimaginably strong, far stronger than Earth's, perhaps even orders of magnitude greater. So, could such magnetospheres exist? The answer is a tentative maybe. Pulsar planets are often theorized to be unusually metal-rich. If they formed from the fallback material of a supernova, they would contain abundant heavy elements like iron and nickel, exactly the kind of materials needed to generate powerful dynamos. If these planets are massive, like Poltergeist and Phobiter in the Lich system, their cores could be large enough to sustain vigorous convection and rotation, fueling a magnetic field stronger than Earth's. In principle, such fields could create magnetospheres robust enough to deflect at least some of the pulsar's particle bombardment. However, there are complications. A pulsar's particle wind is not just stronger than the solar wind, it is billions of times more intense. To truly protect against such a storm, a pulsar planet's magnetosphere would need to be immense, stretching far into space to intercept charged particles before they reach the surface. Whether planetary dynamos are capable of producing such gargantuan shields is uncertain. Even Earth's magnetosphere, though effective against the solar wind, is occasionally overwhelmed by strong solar storms, leading to atmospheric stripping on a small scale and damage to satellites. A pulsar wind would be far more destructive, and it is unclear if any magnetic field could remain effective against it for billions of years. Another issue is the pulsar's radiation. While a magnetosphere can deflect charged particles, it cannot block electromagnetic radiation like gamma rays and X-rays. These high-energy photons would pass through unhindered, bombarding the planet's surface no matter how strong the magnetic shield. In other words, a pulsar planet might resist the particle wind with a powerful magnetosphere, but it would still be scorched by deadly radiation. Any chance at habitability would depend not only on magnetic protection, but also on subsurface refuges, where rock layers could absorb or scatter the penetrating rays. Still, the possibility of magnetosphere protection should not be dismissed. Even partial shielding could make a difference in determining how long a planet can retain volatiles, whether surface materials can survive, and whether underground pockets of water or chemicals remain intact. A strong magnetosphere might not make a pulsar planet habitable, but it could slow the pace of atmospheric erosion and surface stripping, allowing the planet to endure in a less degraded state for longer periods of time. In this sense, magnetic protection might explain why pulsar planets still exist billions of years after their formation. Without such shields, they might have been entirely destroyed long ago. Speculation about magnetospheres also ties into broader debates about exotic planetary compositions. If pulsar planets are unusually rich in heavy elements, their dynamos might be more efficient than those of Earth-like worlds. In extreme scenarios, theorists have even suggested the existence of supermagnetized planets, where magnetic fields are orders of magnitude stronger than Earth's. Such planets would not only resist particle winds more effectively, but might also interact with the pulsar's own magnetic field in complex ways, producing phenomena far beyond what we can observe in the solar system. Imagine auroras 1,000 times brighter than anything on Earth, flickering constantly across the skies of a dead world lit by a dead star. And yet, we must remember the limits of our knowledge. No one has directly measured the magnetic fields of pulsar planets. The entire discussion remains theoretical, built from extrapolations about composition, size, and dynamo physics. For now, the role of magnetospheres in pulsar planet survival remains an open question, one that future instruments may help resolve. If we could detect even faint signatures of magnetic activity, perhaps in the way particles interact with a planet's surroundings, we might learn whether these worlds are truly shielded or whether they endure through sheer, stripped-down resilience. In any case, magnetosphere protection emphasizes an important theme. Pulsar planets are not merely anomalies, but case studies in the extremes of planetary survival. They force us to imagine worlds where protective mechanisms must be pushed to their limits, where survival depends on the interplay of gravity, density, and magnetic force against overwhelming cosmic violence. This discussion of magnetospheres naturally leads to the broader role of debris in these systems. After all, many pulsar planets may not exist solely because of shielding mechanisms, but because of the raw material left over after the supernova. The fallback debris that gathers around a pulsar could not only give birth to new planets, but also influence their long-term survival, acting as both a resource and a hazard. To truly understand pulsar planets, we must next examine the role of these debris disks in shaping their existence. The idea that planets can exist around pulsars is, on its own, astonishing. But when scientists began thinking deeply about how these worlds might arise, attention quickly turned to one of the most fascinating byproducts of stellar death: debris disks. These disks, composed of leftover matter from the supernova that birthed the pulsar, may hold the key to explaining how new planets can form in such unlikely environments. In essence, debris disks represent a form of cosmic recycling, where the violent death of a massive star does not mark the end of planetary formation, but the beginning of a second act in which new worlds emerge from the ashes. When a massive star undergoes core collapse, the explosion hurls vast amounts of matter into space. While much of this ejecta travels outward at extraordinary speeds, some of it lacks the velocity to escape the intense gravity of the newly formed neutron star. This matter falls back, circling the compact remnant and eventually settling into a rotating disk. Astronomers call this a fallback disk, and its existence has been supported by both theoretical models and occasional observational hints. Much like the protoplanetary disks that surround young stars, fallback disks can serve as nurseries where planets are born. The difference lies in their composition. While young stellar disks are primarily made of hydrogen and helium, the fallback disks of pulsars are rich in heavy elements: iron, silicon, carbon, oxygen, and nickel, materials forged in the fires of the supernova itself. This chemical richness gives pulsar debris disks an entirely different potential for planet building. Instead of forming gas giants or ice giants, pulsar systems are far more likely to produce rocky planets, dense and metal-rich. The Lich system is a perfect example. Draugr, Poltergeist, and Phobiter almost certainly formed from a disk of fallback material, gradually clumping together over millions of years. The orbits of Poltergeist and Phobiter, in particular, show resonance patterns that strongly suggest they grew from a shared disk, their gravitational tugs on one another locking them into predictable rhythms. This kind of orbital harmony would be nearly impossible if the planets had been captured randomly. It is much more consistent with formation in a structured debris disk. The process of planet formation in these disks would likely mirror, in broad strokes, the processes that shaped our own solar system. Small dust grains and rocky fragments collide and stick together, forming larger bodies called planetesimals. Over time, repeated collisions and gravitational attraction cause these planetesimals to grow into full-fledged planets. The key difference is that pulsar disks would be far smaller and shorter-lived than those of young stars. The amount of fallback material is limited, and the harsh radiation of the pulsar could disperse the disk over time. This means that pulsar planet formation must happen quickly, on timescales of millions, not billions of years. That such planets exist at all tells us that planet formation can be far more rapid and versatile than once thought. What's remarkable about debris disks is their dual role as both a hazard and a resource. On one hand, they provide the raw materials for new planets, recycling the matter blasted outward by the supernova into coherent worlds. On the other hand, they represent a dangerous environment in which collisions are frequent, radiation is intense, and gravitational interactions can be destabilizing. Planets forming in such disks must contend with not only gathering mass, but also avoiding being destroyed by impacts or pulled too close to the pulsar. That any planets emerge from this chaos is a testament to the resilience of gravity and the tendency of matter to clump and organize itself, even under extreme conditions. Astronomers have looked for evidence of debris disks around pulsars beyond the Lich system, and while they are not common, there are tantalizing hints that they exist. In some systems, excess infrared emissions, radiation that could be explained by the presence of warm dust, have been detected, suggesting that disks of material still circle certain pulsars. These discoveries bolster the theory that pulsar planets are not complete anomalies, but the rare products of specific conditions where enough fallback material was retained to build worlds. The rarity of such disks also explains why pulsar planets themselves are so rare. Not every supernova leaves behind enough debris, and not every disk endures long enough to form stable planets. The role of debris disks also ties into broader astrophysical questions about recycling in the cosmos. Supernovae are known to enrich the interstellar medium with heavy elements, seeding the galaxy with the materials needed to form future stars and planets. But in pulsar systems with debris disks, that recycling happens on a local scale. Instead of dispersing entirely into the galaxy, some of the star's material is reconstituted into planets almost immediately, orbiting the remnant of the very star that created it. In this way, pulsar planets are not just survivors of destruction, but direct products of it, living monuments to the cycle of death and rebirth that governs the universe. The presence of debris disks also carries implications for the physical nature of pulsar planets. Because these disks are dominated by heavy elements, the planets that emerge are likely denser, more metallic, and perhaps even more exotic than those in ordinary systems. The possibility of diamond-rich interiors, ultra-dense iron cores, or unusual mineral compositions becomes much more likely when the building blocks are forged in supernovae. Such compositions would help explain the extraordinary resilience of pulsar planets against radiation and particle bombardment, as dense, metallic planets would resist erosion far better than lighter, volatile-rich worlds. Yet, debris disks remain enigmatic. We cannot observe them directly in most cases, and their evolution is still poorly understood. Do they always form after supernovae? How long do they last before dispersing? Under what conditions do they lead to planets, rather than simply evaporating into space? These are questions astronomers continue to investigate. Future telescopes, especially those capable of detecting faint infrared or sub-millimeter emissions, may reveal more disks around pulsars and help us understand why only a handful produce planets. Ultimately, the role of debris disks in pulsar systems demonstrates the adaptability of the cosmos. Where one might expect only emptiness and destruction after a supernova, nature finds a way to create again. Matter that could have drifted away into interstellar space instead organizes into coherent worlds, recycling catastrophe into stability. Pulsar planets, therefore, are not merely curiosities. They are reminders of the universe's ability to take even its most violent moments and transform them into seeds for new beginnings. And yet, as extraordinary as debris disks are, they do not appear around every pulsar. This rarity may be the very reason why pulsar planets are so unusual compared to the thousands of exoplanets discovered around ordinary stars. Which brings us to the next question. Just how rare are pulsar planets in the grand census of worlds we've found so far? And what does their rarity tell us about the conditions required for their formation? When we step back and consider the larger picture of exoplanetary science, one fact about pulsar planets stands out above all others. They are extraordinarily rare. In the 3 decades since the Lich system was first discovered, astronomers have identified more than 5,000 confirmed exoplanets orbiting stars across the galaxy. These planets span an incredible range, from hot Jupiters and icy giants to rocky Earth-like worlds and super-Earths, but only a handful orbit pulsars. Out of thousands of systems, the confirmed tally of pulsar planets barely rises above single digits. This rarity underscores just how improbable their existence really is, and it forces us to ask why so few pulsar systems manage to host worlds at all. There are several reasons pulsar planets are rare, and the first is rooted in their violent origins. A supernova is not just destructive, it is catastrophically so. When a star explodes, it releases as much energy in a matter of seconds as the sun will emit over its entire lifetime. The resulting shockwaves, radiation, and gravitational collapse all conspire to annihilate or eject any pre-existing planets. While some theories suggest that planets could survive this chaos, the overwhelming likelihood is that most are destroyed outright. For a planetary system to remain intact after such an event would require extremely specific circumstances, such as planets being located at just the right distance to avoid vaporization, yet still remain gravitationally bound. The odds of this alignment are vanishingly small, which is why the survival scenario cannot account for many pulsar planets. The second reason lies in the fallback disk hypothesis. While it provides a compelling explanation for how new planets can form around pulsars, not every supernova produces a fallback disk substantial enough to give rise to planets. In many cases, the material either escapes into interstellar space or is swallowed back into the neutron star. Only in rare situations does enough debris linger, cool, and stabilize into a disk capable of accreting planets. Even then, the window of opportunity is short. Pulsars emit strong winds and radiation that can disperse material quickly, so planet formation must happen rapidly. The number of systems where all of these conditions align is incredibly small, further narrowing the chances of pulsar planets forming. Third, detection biases play a role. Pulsar timing is one of the most sensitive methods for detecting planets, capable of identifying even moon-sized bodies, but not all pulsars are suitable for this kind of observation. Some pulsars emit irregular or noisy signals, making precise timing impossible. Others are too faint or too distant to study in detail. This means that even if pulsar planets exist in greater numbers than currently confirmed, we may lack the ability to detect them. Still, after decades of careful monitoring of many pulsars, the fact that only a few planetary systems have emerged suggests that they are genuinely rare, not simply hidden from view. Another factor is the environment pulsars inhabit. Many neutron stars are located in dense stellar regions, such as globular clusters or near the galactic core, where gravitational interactions with other stars can easily disrupt fragile planetary orbits. Even if planets form or are captured, they may not last long before being perturbed into instability and ejected. The Methuselah planet, orbiting both a pulsar and a white dwarf within a globular cluster, is a remarkable outlier precisely because it has managed to remain stable in such a chaotic environment. Most systems in similar regions likely lose their planets to gravitational chaos long before we could detect them. The rarity of pulsar planets also emphasizes just how special the known examples are. The Lich system, with its trio of rocky worlds, is unique in demonstrating that multiple Earth mass planets can orbit a single pulsar in stable, resonant configurations. The Methuselah planet, in contrast, shows that giant planets can exist around pulsar binaries and endure for billions of years. These examples are not just oddities, they are crucial data points that stretch the boundaries of planetary science. By studying these few rare systems, astronomers gain insights into extreme forms of planet formation and survival that could never be gleaned from the thousands of more ordinary exoplanets. It is also worth noting the symbolic role of pulsar planets in the history of science. The very first confirmed exoplanets were discovered around a pulsar, not a sun-like star. At the time, this was an incredible revelation, one that proved planets exist beyond the solar system. And yet, despite being the pioneers of exoplanetary science, pulsar planets have remained among the rarest class of worlds ever found. In some sense, they are both the beginning of the field and one of its strangest mysteries. Anomalies that opened the door to discovery but then receded into obscurity as astronomers found more abundant planets around main sequence stars. Their rarity carries a profound implication. Pulsar planets are not representative of the galaxy's planetary population. Instead, they are exceptional cases, cosmic accidents where the right conditions aligned to produce unlikely survivors or reborn worlds. This makes them scientifically invaluable because they highlight the outer limits of planetary possibility. If planets can exist around pulsars, they can exist in almost any environment, reminding us that the universe is endlessly inventive. But rarity is not the end of the story. The fact that pulsar planets exist at all forces scientists to rethink fundamental assumptions about planetary formation. Traditionally, planets were thought to form only in the early, peaceful stages of stellar evolution, when young stars were surrounded by nurturing disks of gas and dust. Pulsar planets show us that this is not the whole picture. Planetary formation, it seems, can also occur in the aftermath of chaos, under conditions once thought impossible. This leads us naturally to the next question. What do pulsar planets teach us about planet formation theory as a whole? And how have they expanded our understanding of how worlds can arise in the universe? When pulsar planets were first discovered in the early 1990s, they didn't just surprise astronomers, they completely upended the way scientists thought about how planets form and evolve. Up until that moment, the prevailing wisdom was that planets could only form in the calm, predictable environment of a young star surrounded by a protoplanetary disk of dust and gas. That idea made sense. Stars ignite from collapsing clouds of gas, and the leftover material flattens into a rotating disk. Over millions of years, dust grains within this disk collide, stick together, and grow into planetesimals, eventually forming the planets, moons, and smaller bodies we see in systems like our own solar system. In this framework, planetary systems were thought to be the byproducts of stellar birth, orderly worlds forming in the aftermath of stellar creation. But pulsar planets turned that idea upside down. These worlds orbit not young stars, but dead ones. Their parent stars have already exploded in catastrophic supernova, unleashing destruction that should have vaporized or ejected any pre-existing planets. By all expectations, pulsars should have been barren, gravitational tombstones of stellar death. And yet, pulsar planets exist. Their very presence proves that planetary formation and survival are not confined to peaceful stellar nurseries. Instead, they can also occur in the wreckage of stellar death, showing that the universe is far more versatile and creative than we once imagined. This has forced scientists to radically expand their theories of planetary evolution. Instead of a single pathway, we now recognize multiple potential routes by which planets can come into being. The classic route, formation in protoplanetary disks around young stars, still explains the vast majority of planets discovered so far. But pulsar planets reveal at least two additional pathways. One, survival through destruction, where a planet somehow endures the unimaginable violence of a supernova, and two, rebirth after destruction, where new planets form from fallback material in a pulsar's debris disk. Both scenarios are extreme, but both are now firmly part of the scientific conversation because the data demands it. Consider the survival pathway. For a planet to remain intact during a supernova, it must be at just the right distance from the progenitor star. Too close, and it is obliterated by shockwaves, radiation, and gravitational collapse. Too far, and it may be ejected from the system entirely as the star loses mass and its gravitational pull weakens. The fact that planets like the Methuselah planet exist suggests that, in rare cases, survival is possible. Such worlds may have endured billions of years of chaos, adapting to new orbits as their host stars transformed into neutron stars or white dwarfs. This possibility expands our notion of planetary durability, showing that worlds can persist under conditions once thought fatal. Now consider the rebirth pathway. The fallback disk model demonstrates that planetary formation can occur not only at the beginning of a star's life, but also at its violent end. In this scenario, the supernova's ejected material partially falls back toward the pulsar, forming a disk of enriched heavy elements. From this disk, new planets can form rapidly, creating second-generation planetary systems. This is revolutionary because it shows that planetary formation is not a one-time process tied exclusively to star birth. Instead, planets can be born in multiple phases of stellar evolution, even in environments we would have once dismissed as hopelessly hostile. Pulsar planets are, quite literally, recycled worlds. These revelations have profound implications for how we think about the abundance and diversity of planets in the universe. Before pulsar planets were discovered, it was assumed that most planets would resemble those in our solar system, formed in calm environments around sun-like stars. Today, we know that planets can exist in a dizzying variety of contexts, around red dwarfs, white dwarfs, binary systems, and yes, even pulsars. This means that planetary evolution is not limited to a narrow set of conditions, but is a fundamental feature of the cosmos, capable of occurring wherever matter, gravity, and time intersect. Pulsar planets extend this principle to its extremes, proving that even the wreckage of stellar death can give rise to new worlds. The implications also ripple into questions of habitability and the search for life. While pulsar planets themselves are almost certainly inhospitable, their existence demonstrates that planetary systems are more common and resilient than once thought. If planets can arise even after catastrophic stellar death, then planetary formation is not just a fragile, delicate process. It is robust, adaptable, and perhaps inevitable given the right conditions. This strengthens the argument that planets may be nearly ubiquitous throughout the universe, appearing in places we would never expect. For astrobiology, this is a crucial lesson. The potential habitats for life may extend far beyond the safe zones we once imagined. Another key implication lies in planetary composition. Because pulsar debris disks are dominated by heavy elements forged in supernovae, pulsar planets may be fundamentally different from typical terrestrial planets. They could be unusually metal-rich, with massive iron cores or even diamond-rich interiors. This forces scientists to broaden their classification schemes and consider exotic planetary types that do not fit into the neat categories of rocky, gaseous, or icy. In other words, pulsar planets remind us that the diversity of planetary chemistry is far greater than the limited sample of worlds in our solar system might suggest. Finally, pulsar planets challenge us to rethink the long-term evolution of planetary systems. Traditionally, planets were seen as passive participants in stellar life cycles, forming, orbiting quietly, and eventually being consumed when their stars die. Pulsar planets flip that narrative. They show that planets are not always destroyed by stellar death, and in some cases, new planets can arise afterward. This suggests that planetary systems are not static, but dynamic, capable of regenerating and reorganizing themselves even after catastrophic disruption. Planetary evolution, therefore, is not a simple one-way path from birth to death, but a cyclical process where destruction and creation are intimately linked. In short, pulsar planets have forced scientists to rewrite the rules of planetary science. They prove that planets are more resilient, versatile, and diverse than we ever imagined. They demonstrate that planetary formation is not restricted to the calm beginnings of stars, but can also occur in the violent aftermath of stellar death. They expand our understanding of where and how worlds can arise, reminding us that the universe is endlessly resourceful in creating complexity out of chaos. And while pulsar planets are rare, their very rarity makes them scientifically priceless. Each one is a natural experiment, testing the boundaries of planetary theory in ways that ordinary systems cannot. They remind us that our models must be flexible enough to account for the extraordinary, not just the ordinary. And as our telescopes and detection methods improve, we may find more of these strange worlds, further challenging our assumptions. Which leads us to the final question in this chain of thought. What does the future of pulsar planet research look like? And how might new instruments expand our understanding of these improbable worlds? The story of pulsar planets is one of paradox, resilience, and discovery. They shouldn't exist, and yet they do. They orbit in environments so hostile that no traditional model of planetary survival or formation should allow them, and yet they stand as undeniable proof that the universe does not play by our narrow expectations. The Lich system, with its trio of rocky planets, and the Methuselah planet, a gas giant older than almost any other known world, are testaments to the cosmos's ability to create order from chaos. And while these few examples have already reshaped our theories of planetary evolution, they are almost certainly just the beginning. The future of pulsar planet research promises to reveal far more about these strange worlds, their origins, and their implications for the broader story of planets in the universe. One of the most powerful tools for future pulsar planet research remains the very method that led to their discovery: pulsar timing. Pulsars are among the most precise natural clocks in the universe, their beams of radio emission sweeping across Earth at incredibly regular intervals. Small deviations in these signals can betray the presence of orbiting planets, as their gravitational pull causes the pulsar to wobble slightly around the system's center of mass. Current instruments already measure these variations with microsecond precision, enough to detect planets as small as Draugr, only twice the mass of the Moon. But the next generation of radio observatories promises to push this sensitivity even further, potentially uncovering planets even smaller, with masses comparable to asteroids. The Square Kilometre Array, SKA, currently under construction in Australia and South Africa, will be the most advanced radio telescope ever built. With its unprecedented sensitivity, SKA will be able to detect tiny variations in pulsar timing with a precision unmatched by current facilities. This will allow astronomers to search for pulsar planets with even greater accuracy, mapping out systems that have so far remained invisible. If pulsar planets exist in greater numbers than currently believed, SKA will find them. Even if they remain rare, the telescope will provide detailed measurements of known systems, helping scientists refine models of their mass, density, and orbital dynamics. In short, SKA has the potential to revolutionize our understanding of pulsar planets, just as the Arecibo Observatory did when it uncovered the Lich system 3 decades ago. Beyond radio observations, other next-generation telescopes may also contribute. The James Webb Space Telescope, JWST, though not designed specifically for pulsar studies, could, in principle, detect faint infrared signatures of debris disks around neutron stars. These disks are thought to be the cradles of pulsar planets, but evidence for them remains scarce. Detecting and characterizing such disks would provide direct confirmation of the fallback model and help explain why only a handful of pulsar systems host planets. Likewise, instruments like the European Extremely Large Telescope, ELT, with its 39-meter mirror, could probe distant pulsar environments for telltale signs of dust and heavy element chemistry, offering further insight into the building blocks of pulsar planetary systems. Another promising avenue of research lies in the study of gravitational waves and other subtle signals from pulsar systems. Pulsar timing arrays, PTAS, networks of radio telescopes that monitor pulsars across the sky, are already being used to detect the low-frequency hum of gravitational waves produced by merging supermassive black holes. But these arrays could also reveal new information about pulsar planets. For instance, small irregularities in timing data, if carefully disentangled from other noise, might point to planetary companions. As PTAS become more sophisticated, they could uncover pulsar planets that are currently hidden in the data, adding to the growing census of these strange worlds. The future also holds promise in the field of computational astrophysics. As simulations of supernovae and fallback disks become more detailed, scientists will gain a clearer picture of how pulsar planets might form. Already, computer models have shown that under the right conditions, fallback material can clump together into planet-sized bodies relatively quickly. Future simulations, powered by advances in supercomputing, will refine these predictions, revealing the conditions under which pulsar planets are most likely to arise. This will help astronomers target specific pulsars for observation, focusing efforts on those most likely to host planetary systems. Importantly, pulsar planets are more than just curiosities. They are windows into some of the most extreme physical processes in the universe. By studying them, astronomers can learn not only about planetary formation, but also about the physics of neutron stars, magnetic fields, and stellar evolution. For example, understanding how pulsar winds interact with planetary surfaces and atmospheres could shed light on the behavior of high-energy particles in extreme magnetic environments. Likewise, measuring the compositions of pulsar planets could provide clues about the chemistry of supernova debris, helping us understand how heavy elements are distributed throughout the galaxy. In this way, pulsar planets are laboratories for physics as much as they are anomalies in planetary science. There is also a philosophical aspect to the future of pulsar planet research. These worlds remind us that the universe is not bound by our assumptions of order or habitability. They show us that planets can arise in places where no one expected them, that survival is possible in environments defined by destruction, and that planetary formation is not a single, linear process, but a phenomenon capable of adapting to wildly different conditions. As such, pulsar planets expand our imagination about what is possible. They prepare us for the likelihood that future discoveries will continue to challenge our most basic assumptions. In the decades ahead, as telescopes grow more powerful and techniques more precise, we may uncover more pulsar planets lurking in the data. Some may be small, rocky survivors like those in the Lich system. Others may be massive giants like the Methuselah planet. And perhaps, if the universe is stranger still, we may one day find pulsar planets unlike anything we can currently imagine. Worlds composed of exotic matter, diamond-rich interiors, or even systems that blur the line between planet and star. Each new discovery will add a piece to the puzzle, helping us refine our theories of how planets can form, evolve, and survive in the harshest corners of the cosmos. In the end, pulsar planets are not just anomalies, they are messengers. They tell us that planetary formation is more resilient, more diverse, and more surprising than we once believed. They remind us that even in the ruins of death, new worlds can arise. And with the next generation of telescopes and observational tools, we are poised to uncover more of these strange survivors, expanding not only our understanding of planetary science, but also our appreciation for the universe's endless capacity to astonish. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.